Hello everybody, today we are making a video to show the final project for our signals processing course. And what we have here is basically an inverted pendulum problem with this nice diagram on the board here. And our problem is going to consist of a flexible beam with a mass at the top, and this will actually be an unstable system, so it will fall to either end. It does not have enough rigidity to stay up by itself. And the data from that will be processed through a strain gauge, which is going to be going back to our magical black box over here, which contains a servo that will be actuating this cart back and forth to try and keep this mass from falling off to either side.
At the heart of our project is the inverted pendulum, which is a dynamically unstable system. And if we go to look at dynamic stability, first here, we can see a stable system, and for a stable system, basically imagine a ball that is within a valley, and if you displace it off to the side, when released, the ball is going to return back to its initial position, probably after oscillating a little bit back and forth. Now moving on to what is called a neutrally stable system, if we displace the ball off to the side, it is basically going to remain in that displaced position. And finally, an unstable system would be a ball on top of a hill. Now, as soon as the ball moves off to the side, it's going to continue falling and never come back. And that is basically exactly what the inverted pendulum is here. You can see as the pendulum displaces off to the side, it will just keep bending.
In order to measure the deflection of our beam, we use a strain gauge. As you can see here, the strain gauge is a one-directional strain gauge attached with a positive wire, pictured with the red, and a blue ground wire. In order to create this, we glued our strain gauge onto the beam, and the leads were soldered on as well. If you're doing this yourself, you want to be very careful because the strain gauge is delicate. Here we have our very own strain gauge that we glued onto our beam itself. The strain gauge measures strain by a change in resistance. As the deflection of the beam occurred, there was either a compression or tension. As the wires became longer, the resistance increased, or as they were in compression, they decreased, decreasing resistance, which fed into our next system.
Alright, so now here we have a Wheatstone bridge. And the purpose of our Wheatstone bridge is going to be to take the change in resistance that is coming from our sensor, which basically is our strain gauge, and it's going to be comparing it to the resistance of this circuit here to create basically a voltage signal instead of a resistance. Now, a Wheatstone bridge is an active circuit. It requires a input voltage here from these two legs. You can see the E plus and the E minus. And here you have two different legs, and when the bridge is perfectly balanced, you're going to have the same resistance on this top leg versus the bottom leg, and therefore it's going to be just like a parallel circuit where you're going to have the same voltage going through both of them. Now, on the top leg here, basically you have these two resistors here, but the second one has been split up into two more, and this part here, as you can see, is a potentiometer. The potentiometer is there because when resistors are manufactured, they're not always exactly the same. I mean, we do have very good tolerances now in manufacturing, but still, it doesn't come out exactly the same. And this potentiometer is there so that once you finish constructing this Wheatstone bridge, you can adjust it and make sure that this is balanced so that there isn't a difference in voltage between the top and the bottom. Now, the actual measurement that is going to be taken is from this top and bottom circuit here. You can see the N plus and the N minus. And when your strain gauge gives you a different resistance, now you have basically a voltage potential between that top and bottom. And that is the signal that is going to be fed out of the Wheatstone bridge and go into the INA, which is coming up next.
So the voltage signal from the Wheatstone bridge is passed into the instrumentation amplifier. From the Wheatstone bridge, it's a very small signal, so we need to amplify it. So it comes in at pins 3 and 2. But because the instrumentation amplifier is an active circuit, we have to feed in a power source too, which comes in at pins 7 and 4. Now, the instrumentation amplifier we use is an INA126, which contains two operational amplifiers and an arrangement of resistors that allow us to adjust for a gain, a desired gain. So you can see that the equation here is how we determine how much we are increase in our voltage. It's based on the voltage we feed in, the difference in the voltage we feed in, and the gain value. The gain value is set by this equation here, which is basically determined by an external resistor, so which is out here outside the instrumentation amplifier. For our situation, we use two potentiometers to dial in the resistance so we could get our desired gain value. So the voltage comes in, goes through this magical INA 126, and comes out bigger, so it can be passed on.
This is our PSOC 5 starter kit that's given to us in class. It stands for Programmable System on a Chip, and it's made by Cypress. When we open it up, we have our installation software, which comes loaded with our PSOC programmer, where we input all the code in. We have our PSOC board itself. We have a 9-volt battery, which it comes with to power. We also have a USB cord, which we can use to power it and also transfer the data from the computer to the PSOC. When we take a closer look at the PSOC is equipped with multiple different sensors. We have the cap sensor, we have an accelerometer, we have the proximity sensor, and also a thermistor. The power regulations for the PSOC is 0 to 5 volts, so we cannot put in less than 0 volts or we'll fry it, along with more than 5 volts, and the same thing will happen. With the 9-volt battery, the input prongs are attached to a voltage regulator, which dumbs it down, along with it only gets 5 volts from the USB itself. Looking at the PSOC chip itself, it has a faster processor for a higher resolution. It also has 100 pins, which are programmable for a variety of different applications. This gives us an advantage over multiple other microcontrollers because their chip or their pins are actually preset. Turning it over, we see our pins. This is where we input and output our signals. We get an output signal from, an input signal from our strain gauge, which is an analog controller or analog signal. So the PSOC chip has to actually program a analog to digital converter, which we're going to talk about later, code it through, and then send out a PWM signal to our servo arm.
An ADC is a device that converts a continuous physical quantity into a digital number that represents the quantity's amplitude using voltage. Right, the results are digital values that convert continuous into discrete. From this graph, you can see an analog signal, which is a smooth, continuous signal. The blue line represents a signal that's a piecewise, discrete signal, which converts into a digital signal. For our system, we chose a 16-bit analog to digital converter. This gave us 65,535 counts. So with our system ranging from 0 to 6.14 volts, this gave us a resolution of 0.09 millivolts per count. So that meant that even though the strain gauge measures small voltages, we will still be able to detect the change in it.
All right, so now we're going to look at our servo, and for this project we used a high-tech servo, and this high-tech servo required an input voltage between 4.8 to 7.2 volts, PWM voltage 3.3 to 5.5 volts, and the pulse width for the minimum value was 1.1 milliseconds, maximum at 1.9 milliseconds, with centering at 1.5 milliseconds. The timing for the signal has to be between 15 to 20 milliseconds if you want to do the power saving mode. However, for this project, there were no power requirements, so we basically did a continuous signal. Now, looking here, our servo requires a 50% duty cycle, and that is basically the pulse width divided by the period is equal to 1/2. And you can see on the graph here, here's the pulse width, and here is the period showing 1/2 for the 50% duty cycle. And you have to remember that when the pulse width is increased, the period must be increased by twice as much to maintain that 50% duty cycle expected by the servo. Now onto the servo itself, with a 1.1 millisecond command, you're going to get a position about here. 1.5 would be in the center, and 1.9 is going to be the extreme on the other end. And finally, moving on to the circuit with the servo and the battery as well. You can see here that we are using a 2-cell LiPo battery that has a voltage greater than 7.4 volts that is passed through a 5-volt regulator that is then sending the power to the servo. And also here the servo, the LiPo battery, and the PSOC all must share a common ground so that the PWM signal coming from the PSOC to the servo can be properly sent.
This is our inverted pendulum system. As you can see, we start with the cart, where we have our beam that is, our strain gauge is glued on as before, and our mass that we put on top to get the deflection that we need for the instability. The signal is produced through the wire all the way to our Wheatstone bridge that we talked about earlier into the instrument amplifier, where the signal gets produced through the PSOC, which is our microcontroller, where the PWM signal gets coded. And from there, the signal gets exported out to the servo arm, which controls our cart rocking back and forth. As you can see, the servo arm has been extended to get a translational or more translational distance for the cart to keep the mass centered. This is how we related beam deflection to the servo output. You can see right now we're starting with our voltage from the MIDAC. It's supplying a 0 to 5 volt voltage to the instrumentation amplifier. Our signal is getting produced from the beam into the amplifier and not to our PSOC, but to our multimeter, which is displaying the voltage output. First, though, we need to make sure that the beam deflection in both directions is outputting a positive voltage, because the PSOC does not accept negative voltage. So as you can see, when we bend the beam to one of its maximums and to the minimums, we are still in the positive voltage. And to relate beam deflection to voltage change, what we did was bend the beam in known increments or known angles and plotted the change in voltage, and we came up with this plot. And from this plot, we came up with an equation to relate the beam deflection to the servo arm.
Okay, so one of the things we had to do was calibrate the servo. So we knew that the range should be approximately 1,900 to 1,100 counts, because based on the 1.1 to 1.9 millisecond pulse width. And after some empirical testing, we found that the actual range was 1,889 to 1,149, which is in 16-bit counts. And that corresponds to a servo angle of 33 degrees to 166 degrees. Once we found the maximums of the servo angle, we tested a variety of range of points in between, measuring the angle of the servo displacement with a protractor and recording the corresponding PWM counts. This gave us a linear relationship, providing a relation between the PWM counts required and the servo displacement angle.
And so now we're going back to our algorithm. So we're going to be explaining how we have here our beam angle, which is measured from center top. We have theta S, which is measured from servo center top, and then S angle, which is measured from the zero angle up to the maximum or whatever deflection of the servo we're at. We also have the length of the servo arm and the length of the beam. So moving on to the actual equations that relate all these things together, we have a delta beam distance, which is calculated as the length of the beam times sine of the beam angle from displacement from, or the angle of the displacement from the center. We multiply that times a negative value because we were getting it where the angle was actually giving us the wrong direction of the beam distance, and so the servo was trying to pull it in the wrong direction, so we threw in a negative sign to solve the problem. We also have 1 times 1.7 because we actually want the servo to push the cart a little bit past where it would be having the mass on top of the beam be underneath the bottom of the beam, because we want the mass to actually come back towards the center rather than continuously start going towards the servo maximum. And then we have an accumulated beam distance, and the reason we went with an accumulated beam distance is because if we actually did it the other way before, where we had just a delta beam distance as calculating our servo angle, and what would happen is the beam would deflect, and then the servo would deflect to push the beam back upright. And at that point, it would say, okay, well now my delta beam distance is 0, and so the servo would reset back to 0 because it's trying to do no change, and it would actually pull the beam back. So we use an accumulated beam distance to solve that problem, so that when the beam falls over, you get it back to center, and then it says I need to move none. It says, well, I need to stay where I am instead of moving back to center. So once you get the accumulated beam distance, simple trigonometry tells you that theta s is going to be equal to the inverse sine of the accumulated beam distance over the length of the servo arm. And then we had to do a conversion because we calibrated the servo angle to the 0 rather than to the 90. And so this is 80 plus 87, and the reason 87, not 90, is because the furthest we can get the servo to go down relative to level of the actual physical servo was 3 degrees. Going into our software, I'm going to be using different colors to refer to different things. So purple refers to methods that were predetermined in the PSOC. Green refers to methods that we created ourselves. Blue are the pseudocode, and objects and numerical values are going to be presented in red. And so once our main function begins, we're going to first move into the initiate function. Alright, so for our initiate function, the first thing it does is it checks to see if we've already initiated before. Then the next thing it does is it starts up all of the analog digital converter, PWM, the clocks, and moves on to command the PWM to 90 for the servo. Basically, we want to start with the servo facing up so that it doesn't move around once we start actually trying to read in the strain gauge value. So we have a 1 second delay to make sure that the analog to digital converter has time in order to actually determine the value output from the strain gauge. And then if the ADC converter has a strain gauge value for us, then we set the center value equal to that value. So that gives us our center reference point for later to tell which way the beam's bending. And we have a few values we initialize here. PWM per degree is calibrated from the servo, so basically that tells us what degree the servo needs to be and what PWM signal needs to be out. It's a ratio. And then init we set equal to 1 so that it will not go through this whole process again when it runs through the code again. And we have a 2 second delay to make sure that we're ready for the cart to start moving on us. After our 1/4 second delay, we're going to have a function that gets the angle of the beam from the strain gauge. Alright, so for our get beam angle function, we're going to initialize a double called beam angle, which we're going to later return as the output of the function. So the next step is to move into the for loop, which goes from values of 1 to 100, where it checks for if the analog to digital converter has a value that it can actually give us, and if it does, then the output becomes the analog to digital conversion output. Then we calculate our voltage difference by multiplying our ratio of voltage over the number of counts for a 16-bit analog digital converter by the output that we've just found minus the center value we took in the initiate function. We then calculate the actual beam angle by using our calibration that we did earlier for the beam, which ends up being about 440 times the voltage difference, and then you see plus 90, which is the actual part of our calibration, and we subtract 90 so that it's relative to 0 when it's straight up and down. And then if I is equal to 100, then we are going to return the beam angle. After we get the beam angle back, we're going to pass it into the get beam distance function so we can figure out how far the cart needs to move. Okay, and so for the get beam distance function, we're passing in the beam angle from earlier, and now we initiate a value called get beam distance, which we're going to be returning at the end of this. So the delta beam distance is equal to negative 1.7. It's larger than 1 and negative because the beam deflection was going in the opposite direction of the actual output distance that we were estimating, so the servo was moving the wrong way. So this accounts for that. as well as the 1.7, we want the beam to actually, we want the cart to understand that it needs to move a little bit further than the actual delta beam distance in order to bring the mass back to the center. So that gets multiplied times 1.7 times the beam length and sine of the beam angle, which gives us the translational distance of the cart. And then of course we return the beam distance.
And then we're going to calculate the accumulated beam distance by adding the cart displacement, which is the delta movement of the beam, to the accumulated beam distance from before. After determining the accumulated beam distance, we pass it into the get servo angle so we can actually figure out the angle that we need to command the servo to.
Okay, and for our get servo angle, we're going to be passing in the distance that the beam has moved. We're going to initialize our values of theta s, s angle, and ds. And to explain those kind of angles, theta s is the angle from 90 to the servo arm angle. S angle is from our 3-degree angle because the servo can't go to 0 in our PWM signal. So from the 3-degree up to where the servo has moved. Coming back, theta s is calculated as the arc sine of the beam distance, the distance the beam has moved over the servo arm length. It's basic trigonometry, and then you multiply times 180 over pi because we're working in actual degrees for as far as all of our code has been written in. And then S angle is calculated by adding 87 degrees, 87 instead of 90 because of that 3 degrees offset. And so that gives us the servo angle we need to command, and then we return the servo angle.
And then we take the target angle and we put it into our command PWM function, which will actually move the servo into the appropriate position to balance the beam.
And so for our commanded PWM function, we're going to be passing in the angle, which is the target angle from the previous method. We're going to calculate the pulse width, which is going to be a subtraction from the maximum PWM value, which corresponds to the 3-degree angle in our servo. And we're going to compare it to the angle that is the target angle from earlier. Now we have a ratio in here, so we can convert the angle into a PWM value. So we're comparing a PWM value to a PWM value instead of a PWM value to an angle. So we're not comparing apples and oranges. Then we have the period, which is calculated as the pulse width plus 1 times 2. The plus 1 comes in there because there's a weird part of how you have to double the pulse width, and then you subtract 1 at the end because, as it turned out when we were looking in PSOC, when you have a value of a PWM and you try and set it equal to what you think would actually be the exact number for the number of milliseconds, it's slightly off. So that was just part of the calibration with the PSOC code. It's probably where you start at 0 instead of 1. And then we have a method from the PSOC, which is default, and this goes into the boxes of the PWM function. And so you have the PWM write period, which gives the period to the method that the PSOC has, and you have PWM write compare, which gives it the pulse width. It's the value it's comparing to the period. And then we had a return pulse width here, and we originally had that for calibration, but we no longer use it, so this is a 0 value.
And so here we have the blocks that are pre-programmed into the PSOC. So they give us an analog digital converter shown on top and a PWM block, which is shown on the bottom. The titles are important when you're coding because ADC underscore delta sig underscore 1, that's actually what you call on, and you call on methods that are pre-allocated to that type of method. And you can see that the analog digital converter is set to pin 2 and the PWM is set to pin 1, which will be important in a second. And we have a clock associated with the PWM, which is at 1 megahertz. And here is where you can see where we've set those pins, the points on the outside. So you see the green 5 volts is in various places. Pin 1 is on the right-hand side. Pin 2 is on the left-hand side. And that allows us, we were allowed to move them around, but this was the spot we chose because it was convenient physically to put the components onto the PSOC.
Alright, I'm going to talk to you about some of the problems that we encountered while trying to do this project. First of all, when the cart was initially moving, even though we put our servo horn here right in the center, we were still getting it drifting off to the side. So simply we just used a piece of wood to stick underneath the cart and use that as a guide for the wheels. For future projects, it might be good to build a track system that the cart rides on, so you don't have to worry about that. Next that we ran into was the servo arm itself. When it was doing a lot of kind of oscillations back and forth, it was actually breaking, so a more robust servo arm could be constructed. And then the third problem, and probably one of our biggest problems, was the beam itself. The material, this is really like a galvanized mild steel. I would say the same thing that they make heating ducts out of. And as this was shaking back and forth, it was actually changing the shape of the beam. You can see here it's very soft. It's pretty straight right now. And just a simple shake like that, and it's pretty well bent. So maybe look to going to like a spring steel or something so that the beam itself will be able to hold its shape. And we did run into some issues with different modes being apparent depending on the frequency, and that might also be remedied by having a little bit more of a rigid beam. So overall, that was the biggest part of our problem. The mass, it's adjustable here by the number of pennies that we put into it, a couple quarters there for a little extra monetary value, but that could also be refined and a little bit more easily adjusted if you really wanted to, but this does work. And that about sums it up.